Kia ora, it's Bill back again. I want to have a look at pulse width modulation, PWM. So PWM. So what we've got here is I've got these LEDs connected to my microcontroller, and what I've got is I've got a crystal which is 16 megahertz. I've got that feeding a prescaler, and that is feeding timer counter number 2, which is a 0 to 255 counter, and then that is connected to D.3, or it's in its dual mode. It is output compare to B, so that's the pin of the microcontroller, which of course is connected to our FET. What I've got, 16 megahertz prescaler. At the moment, my prescaler, if I have a look for it, is set. Here we go. Oh no, it's set up here in my, here you go, timer 2 prescaler. What I've got is I've got these 2 bits set here, and if I look at the data sheet, those 2 bits in the, let's just make this a little bit bigger, in the data sheet, these are the 3 bits which set the prescaler for timer counter 2, and I've got these 2 bits set here, which means it's divide by 32, so I've got to divide by 32. And so what I've got is 16 megahertz divided by 32 is, of course, 500 kilohertz. So the 500 kilohertz is feeding into the counter. Now the counter counts from 0 to 255. However, there are 2 PWM modes that I want to have a look at. There's fast PWM, and then there is phase correct PWM. And in the fast PWM mode, if you can imagine, the count goes from 0 to 255. In this mode, the count goes up to 255 and then overflows back down to 0, up to 255 and then down to 0. So the period here, this period here, would be, in actual fact, 500 kilohertz divided by 256. Remember, there's 256 counts in this. So if I look at my calculator, I think that works out around about 2 milliseconds, but not exactly. So if I take my calculator and I go 500 kilohertz divided by 256 gives me 2 kilohertz. Yeah, so this would be about a 2 kilohertz pulse coming out of here. Now, the other mode is called the phase correct PWM. Again, the counter goes from 0 to 255. And what happens then is it gets to 255, and then it counts back down to 0 again, and then it counts back up. So what you're getting here is the time period of this signal here is considerably different to that, because they're both being fed with 500 kilohertz. And this is a count of 256, but this is actually a count of 510, because it goes from 0 to 255 and then back down to 0 again and then back up. So there's no overflow to get the extra count, which we would think there might be, but there's not. So it's just 510, it's not 512. So what we've got here is we've got 500 kilohertz divided by 512, which is around about that 1 millisecond. So if I get my 500 kilohertz divided by 510, then what we get is 980 hertz, which has a period of, inverse that, a 1.02 milliseconds. So that's 1.02 milliseconds, right? So this is a 2 kilohertz signal here, and this is a 1 kilohertz signal roughly here. Not quite, but close to it. So let's have a look at this and see what's actually happening. If I get my LEDs and I turn them back on, they're in a dim mode at the moment. I get my oscilloscope and I'll bring it over here and have a look. And this is what we've got, this nice little analog discovery that I'm using. It's got all these neat features, so we can actually see what's going on here. So our time period is 1.021 milliseconds, 979 hertz. And of course, we can just adjust the PWM to what we want it to be in this mode. So I'm just going to adjust that so I can get my LEDs to go quite dim. Okay, so now they're dimming down. But of course, you can't see them flashing. They are flashing on and off, but you can't see them flashing because of the rate at which they're flashing. And that rate is controlled by the divide by 32 and then the count, in this case, count up to 510, which gives us 1 millisecond, so about 1 kilohertz. So they're flashing 1,000 times per second. Our eyes are not able to see that. We can, of course, change the frequency at which is coming out of here by changing the prescaler. So let's just have a look at the prescaler and take, for instance, if I've already prepared this, so I'm just going to comment out that line, put this in as my prescale, which is a divide by 1,000, and I'm going to upload that. So this will be, sorry, this is a divide by 1024. We'll just check that all 3 bits in the data sheet. When I set all 3 bits, I get a divide by 1024. So if I divide by 1024, 16 meg divided by 1024, where's my calculator? Just model this first, 16 megs divided by 1024, so 15 kilohertz. Now again, I'm going to count up to 510, so that to divide that by 510, and that will give me a frequency of about 30 hertz. So this will no longer be 1 millisecond, the inverse of that. It will go down to about 0.032 or 32 milliseconds, 33 milliseconds. Now at that stage, I should be able to see the LEDs flashing on and off. Whether that works with this camera or not, and in a video, I doubt. Okay, but we'll just have a look and see what happens. So what I'm going to do is I'm going to program this now. Having modeled it first, I'm going to check it out in the program. So I've put this in, there's compile, and there we go, and I will now, and let's just see what's going on. So now you cannot see the flashing, okay? You just can't see this flashing, it's actually flickering. I can see it flickering, but because what we've got is we've got this camera resolution and the LED of the camera and 50 hertz and the scanning rates and things, what you're getting is some sort of stroboscopic effect. So you can't actually see it, but we can see it in the scope. So if I go back to my oscilloscope, there we go. Now our signal has changed considerably. There we go. We've now got 30 hertz, or a period of 32.6 milliseconds, and that's about what I said it would be, 32.7 or 32.64, and we're measuring 32.67 milliseconds here as our period. So, but you just can't actually see the flickering of this because of the stroboscopic effects. So that's pulse width modulation. We've got 2 types, fast and phase correct. And the phase correct one, I guess, is probably useful for many applications, because what happens here is that it counts from 0 up to our value, say our value of output compare register 2B. Yeah, well, let's just double check that we understand what is going on here. So we've got an equality here. Check the equality, and this is our output compare register 2B. So what it's doing is it's checking to see when this when the timer count reaches output compare register 2B, and then it's toggling this pin. And I've got that set up so that if I go back down to my initialize the timer, I've got connect output can clear the pin on compare match, which means that what happens is, if here's the voltage of my pin, D.3 or output compare 2B, if that voltage is 0 and there's 5, what's happening is at this point in time, it's clearing it, so it's going to 0. And here's the other point in time, it's going high. So this is what's happening at the moment. So I've got quite a, the pulse is clearing when it gets to when the count gets to output can be registered 2B value, and then it gets up to 255, starts to count back down, and when it gets to output compare register 2B again, it goes high. And so what you can see is, depending on where output compare register 2B is in here, the center of this pulse will always be lined up with the center of this waveform. No matter what the comparison value is, it'll just make it wider and narrower around that center point. So that's our phase correct. Over here, of course, if we've got output compare register 2B value here, then what will happen is that the value will come along, it will go low here, and then it will go high when the counter resets to 0. But so this is not phase correct, it's just always lined up with this point, and this goes wider and narrower. So that's the fast PWM, phase correct PWM. You can get different frequencies. Frequency is set by the prescaler, and the actual triggering point is set by, or the toggling point for the pin is set by this output compare register 2B, which in this case I've shown you is connected to my trim pot. And if I look in my code, I'll find out where that is. It's in the light, one of these transition functions. I'll go into those in a moment. So the light dim, here it is. So it's getting the value of the ADC channel that the trim pot is connected to, and then it's doing some conversion to turn it into an 8-bit number, because of course our ADC values are 10-bit numbers. Right, so I'll stop this one, and we'll go on in another video to the next thing.